So good day everyone. In this session, we are going to discuss some of the questions based on electronic materials and devices. We'll see some of the practical questions and how it can be solved. Okay. So let's see the first question. Let's consider a silicon sample. That means let's say this is my silicon sample and with a unit cross-sectional area. That means your area A is 1. So which is shown in this figure 1, and the whole sample, that means the silicon sample is in thermal equilibrium. Okay. What are the data given here? The sample is placed at room temperature. That is why it is at 300 Kelvin, because room temperature is 27 degrees centigrade. So that means if we can convert it into degree Kelvin, then it is 300 Kelvin. Okay. Now electronic charge we know 1.6 into 10 to the power minus 19 coulomb. Thermal voltage is 26 millivolt, and electron mobility is given 1350 centimeter square per volt second. Okay. So what is the question here asked? That find the magnitude of electric field at x is equal to 0.5 micrometer. And second question is find the magnitude of electron drift current density at x is equal to 0.5 micrometer. You see, in this case, the sample is given a applied bias, that is, and the applied bias is 1 volt across this sample. And if you can see if you can see the sample, so it is from x is equal to 0 micrometer to x is equal to 1 micrometer. So you can see the total length in this length is actually 1 micrometer. Okay. Now, when it is asked that find the electric field at 0.5 micrometer, we need to check what is the condition of the sample. And the condition of the sample is already described in the questions. What the condition? It is said that the sample is in thermal equilibrium. So what does that mean? It means that the electric field, even if we find out at this x is equal to 0.5 micrometer or any place, it will be the same. Wherever we take any length of any, let's say x is equal to 0, x is equal to 0.25 or x is equal to 75, so it will be the same. So if you can calculate its electric field, then its electric field will be, if you can see, as the sample is in thermal equilibrium, the electric field will be nothing but the voltage across the sample and divided by the length or the distance. What is the length here? 1 micrometer. Okay. We have to take the total length. In this cases, because as we know that electric field is the negative of potential gradient. Potential gradient means your your voltage with respect to distance, right? But here we are taking the magnitude part, so that is why it is voltage with respect to the length. So what is the voltage across the sample? It is 1 volt. So 1 divided by, and what is the length here? It is total 1 micrometer. So even if it is asking the magnitude of electric field at x is equal to 0.5 micrometer at the length, at the middle of this, uh, you can see the sample. But the magnitude of electric field, when we have to take the total length. So that is 1 micrometer here. And 1 micrometer, as you know, it is 10 to the power minus 6 meter. So if we can divide, so it is coming to be 10 to the power 6 volt per meter. Or if you can convert it into in kilovolt and centimeter, it is coming to be 10 kilovolt per centimeter. Okay. So we have to take care about the units, whether it is in volt per centimeter or volt per meter. Okay. So in volt per meter, it is 10 to the power 6 volt per meter, and in kilovolt per centimeter, if we find out, then it is 10 kV or 10 kilovolt per centimeter. Okay. Now, if you can go to the next option, that what is the magnitude of the electron deep current density x is equal to 0.5 micrometer. That means here it is asking what is the magnitude of the electron drift current density. Okay, electron different density at x is equal to 0.5 micrometer. So again, as the sample is in thermal equilibrium, we have to use the conventional current density, that is J is equal to sigma E. What is J? J is the current density, sigma is the conductivity, and E is the electric field. Okay, but this conductivity is further can be expressed in terms of electron concentration, charge, and mobility. So let's say if N is the electron concentration, Q is the electronic charge, and mu N is the mobility of electron, then my conductivity will be N Q mu N. Okay, N Q mu N. Here it is showing that the donor concentration is given 10 to the power 16 per centimeter cube. So that means the donor concentration is very high. So we can conclude here that the electron concentration will be equal to the donor concentration here. So here my conductivity will be, so in the place of electron concentration we'll put donor concentration, because here donor concentration is very high, so which we can consider that the donor concentration will be equal to the electron concentration, and Q the charge and mu the electron mobility. So my final answer will be, when we take the exact relation, so your current density J equal to Nd, that is your donor concentration, charge, electronic charge, mobility into electric field. So this conductivity relation we will put it here, and then we get the final current density relation. So if we can put all the value, because donor concentration is given 10 to the power 16 per centimeter cube, and electronic charge is 1.6 into 10 to the power minus 19 coulomb. Mobility is given already, that is 1350 centimeter square per volt second. And electric field, as you know, it is 10 kilovolt per centimeter. So finally, if you can multiply, so finally it is coming to be 2.16 into 10 to the power 4 ampere per centimeter square. So we need to be very careful about the unit. So if we want to convert into ampere per centimeter square, so we have to make it sure all the units will be as per the consideration. So, so correct answer of A is the electric field at x is equal to 0.5 micrometer is 10 kilovolt per centimeter, and the magnitude of electron current density at x is equal to 0.5 micrometer will be 2.16 into 10 to the power 4 ampere per centimeter square. Okay. So I hope this first question is clear to everyone. Then we'll move to second question. The question here is, let's assume electronic charge is 1.6 into 10 to the power minus 19 coulomb. That we know that the charge of electron is 1.6 into 10 to the power minus 19 coulomb. And this is kT by Q, that is 25 millivolt, that we also in other word uh, we if we take where K is the Boltzmann constant, T is the absolute 0 degree temperature, and Q is the electronic charge. So if you can, because all are constants, and if you take the T is equal to 300 degree Kelvin, so if you can take put all the values, then we will find we can get 25 millivolt. Okay, so this is considered to be at room temperature. Okay, so KT by Q is 25 millivolt. Then that is nothing but this KT by Q is also called volt equivalent of temperature also. Okay, in other words, we expressed in terms of its terminology VT. Okay, VT we generally used. Then electron mobility is given, that is 1000 centimeters square per volt second. Now it is asked that if the concentration gradient of electrons injected into a p-type silicon sample is 1 into 10 to the power 21 per centimeter to the power 4. Okay, you see 1 into 10 to the 21 centimeter to the power minus 4. Why it is centimeter to the power minus 4? Because it is concentration gradient. Okay, concentration unit, as you know, per unit volume, right? The numbers per unit volume. But again, concentration gradient, that means with respect to your distance or with respect to your length. So that is why it is the unit is centimeter to the power minus 4. Okay. So here the question is asked, find the magnitude of the electron diffusion current density in ampere per centimeter square taken into consideration if K is the Boltzmann constant and T is the absolute degree temperature. So how we can proceed? We have to see here what is the correct relationship when we want to find out the uh, uh, electron diffusion current density, because here the current density is asking diffusion current density. So what is the relation? So we have to take care of the concentration gradient, diffusion coefficient, electronic charge, and if we take this consideration, we can find out the current density. So the current density can be represented like this relation: Q dn by dx. What is Q? Q is the electronic charge. Dn the diffusion constant for electron. Dn by dx is the electron concentration gradient. Okay. So this dn by dx, that is change of electron concentration with respect to distance. That is dn by dx. Okay. Now this dn further can be write as mu n into Vt, because Vt is nothing but a port equivalent of temperature, that is nothing but Dn divided by mu n. Dn is the diffusion coefficient of electron and mu n is the mobility of electron. Okay. So if you can see this diffusion coefficient, if you can find out, then if you can put the value, because mobility is already given 1000 centimeters square per volt second, then volt equivalent of temperature is 25 millivolt. So 25 into 10 to the minus 3 volt. So your diffusion coefficient will come into be 25 centimeters square per second. Very important, we need to be very careful about the unit of diffusion coefficient. Okay, diffusion coefficient unit is centimeter square per second. Then once dn we can find out, then we can put this value here, because your dn by dx, that is concentration gradient. Okay, your concentration gradient is already given 1 into 10 to the power 21 centimeter to the power minus 4. Okay, so j will be q. Q nothing but 1.6 into 10 to the power minus 19 coulomb, that is electronic charge, and your diffusion coefficient is 25 centimeter square per second, and your this concentration gradient of electron is 1 into 10 to the power 21 centimeter to the minus 1. So with this regard, if you can find this current density and if you can put the value, then it is coming to be 4000 ampere per centimeter square. So as per the question, it is asked that find the magnitude of the electron diffusion current density in ampere per centimeter square. So what is the correct answer? The correct answer is 4000 ampere per centimeter square. Okay. Now next question will go. Let's consider a bar of silicon. So that means here, which is doped with a boron concentration of 10 to the power 16 uh, per centimeter cube. That means boron is a trivalent impurity, right? So when we trivalent impurity is added to a silicon, then it is a p-type semiconductor. So that part is sure. So that is why in the figure it is mentioned p-type silicon. Why? Because of the doping of trivalent impurity, that is here the boron concentration. It is asked that it is, and we can consider that it is assumed to be fully ionized. Let it be exposed to the light, that means it is irradiated with the light here, as shown in the figure 2, such that the electron hole pairs are generated throughout the volume of the bar at the rate of 10 to the power 20 centimeter to the power minus 3 second inverse. Remember, whenever any light is exposed to a semiconductor, electron hole pairs are generally generated. Okay. Now that is a mechanism here. And as per the question, it is mentioned that the electron hole pairs which are generated throughout the volume of this bar is at the rate of 10 to the power 20 centimeter to the power minus 3 second inverse. Okay. Now, there will be definitely a recombination. Okay. So, what is the recombination lifetime? 100 microsecond. Recombination between whom? Electron and holes. Okay. Now, what is that lifetime for this recombination to occur? That is here 100 microsecond, which is given in the question. Now, what are the data? Other data given that the intrinsic iron concentration of silicon is 10 to the power 10 per centimeter cube. That is your intrinsic iron concentration per unit volume, that is per centimeter cube, is 10 to the power 10. And assuming 100% ionization of boron, 100% ionization of boron, if we assume, then the question here is asking find the approximate product of steady state electron and hole concentration due to this light exposure. Here we have to find out the steady state electron hole concentration product of steady state electron hole concentration, and it to be approximate. Okay, to approximate value we have to find out. Okay, so this is the question. So let's see how we can find the solution. You see, boron is the acceptor type doping, as I said. So, and what is the acceptor concentration is here already given 10 to the power 16 per centimeter cube. Okay. Now, it is mentioned here that as per this irradiation with light, the electron hole pairs are generated throughout the volume. So, but at the rate of what? 10 to the power 20 per centimeter cube second inverse. So, let's say I am denoting the as a terminology GOP. Okay, that GOP is nothing but the electron hole pairs which is generated throughout the volume. Okay, so let's say I am denoting it with a terminology GOP, which is equal to 10 to the power 20 centimeter to the power minus 3 second universe. Then, what is the recombination lifetime? 100 microsecond. It is written recombination lifetime is 100 microsecond. So, that means let me that recombination lifetime I denote it as tau, and what is that? 100 microsecond. Then what else? The intrinsic iron concentration is given, and that is 10 to the power 10 per centimeter cube. Okay. So let's say that is Ni, that is 10 to the 10 per centimeter cube. Okay. So what is the question here? Product of steady state electron and hole concentration. We have to find out when it is irradiated with light. Okay. So that means with the exposure of light, you have to find out what is the product of steady state electron hole concentration. Okay. But approximate value. Okay. It can be exact value, but approximate product of steady state electron hole concentration we have to find out when it is exposed to light. So before shining light at thermal, when the sample is in thermal equilibrium, what will be my hole concentration? Hole concentration will be, let's say, I'm denoting as the hole concentration P naught. So that is equal to your acceptor concentration, and that is nothing but 10 to the power 16 centimeter cube. So what will be my electron concentration as per mass action law? So that is nothing but intrinsic carrier concentration square divided by the whole concentration. So intrinsic carrier concentration already given 10 to the power 10. So 10 to the 10 square is 10 to the 20 divided by whole concentration 10 to the power 16. So it is coming to be 10 to the power 4 centimeter to the power minus 3. Okay. So whole concentration is 10 to the 16 centimeter to the minus 3, and electron concentration is 10 to the 4 centimeter to the minus 3. Now this is all before shining of light. Okay. Now after illumination of light, what happens? You see, when there will be illumination of light, as you know, there will be some extra whole concentration will be generated, as well as electron concentration also. So after whole concentration, so if the whole concentration after illumination, if we denote it as P, then it will be P naught plus del P. What is P naught? P naught is the whole concentration before light exposure, and del P is the extra whole concentration which is generated after the illumination of light. And what will be my electron concentration? That is equal to N, which is equal to the N naught. What is N naught? N naught is the electron concentration before the light exposure plus the change in electron concentration. Okay. So due to shining of light, there will be excess carrier concentration. Okay. Now this excess carrier concentration, how we can calculate? Okay. Now already it is mentioned the electron hole pairs are generated throughout the volume of at the rate of what 10 to the power 20 centimeter to the power minus 3 second inverse. And what is the live recombination lifetime? 100 microsecond. So the extra hole electron hole concentration and extra electron concentration, only then we can find out when we multiply these two factors. So it will be GOP into DAL. Okay, so it will be 10 to the 20 into 100 into 10 to the minus 6. So it is 10 to the power minus 10 to the power 16 centimeter to the minus 3. Okay, now this is my we can say the excess carrier concentration, excess hole concentration, and this is my excess electron concentration. Del P my excess hole concentration, and which is equal to the excess electron concentration. So what will be my P here? So what my P, that means the whole concentration after illumination of light will be P naught. What is my P naught? Already calculated. That is nothing but 10 to the 16 centimeter cube. That is 10 to the 16 per centimeter cube. Okay. So that is already mentioned in the question. So 10 to the 16 plus and the excess whole concentration which is generated. So that is 10 to the 16. So 2 into 10 to the power 16 centimeter cube. This is my whole concentration after the light exposure. Now, what is my electron concentration here? The electron concentration will be the same. The electron concentration before the light exposure. Now, before the light exposure, the electron concentration we have calculated 10 to the power 4 per centimeter cube. So 10 to the power 4 plus the extra or the excess carrier concentration of electron, that is 10 to the power 16. So if we can take it as an approximate value 10 to the 4 plus 10 to the 16, so it is 10 to the 16 per centimeter cube. Okay. So what is the question here? It is asking that find the approximate product of steady state electron and hole concentration due to light exposure. That means we have to find out what is my steady state electron hole concentration product after the light exposure. So we have to multiply the electron hole concentration after the light exposure. So if you can see here, the product of steady state electron hole concentration will be able to multiply the hole concentration and electron concentration. So here 10 to the 16 into 2 into 10 to the 16. So it is 2 into 10 to the power 32 centimeter to the power minus 6. Okay. So this is my correct answer for this question. Okay. So next question will go to let's say in this figure. So if you can refer this figure 3, the switch is in position 1. So first initially the switch is in position 1, and steady state condition exists from t is equal to 0 to t is equal to t naught. So that means from time at 0 second you can say to t is equal to some time. So that let's say that time is t naught. Okay. So from 0 second to time at certain time t naught, the steady state condition exists. Okay. Now the switch is suddenly thrown back into position 2. That means previously it was in position 1. Now it is moved to position 2. Okay. Now if this is the case, then find the current through this 10k ohm resistor. What is the current through this 10k ohm resistor as a function of time? From t is equal to 0, we have to convert. So that means we have to find out what is the current through this 10k ohm resistor as a function of time from time is equal to t is equal to 0. And also we have to sketch the current with respect to time. That means time will be your independent variable and current will be your dependent variable. So you have to plot a sketch. That means you have to sketch current with respect to time and showing that the magnitudes of current at t is equal to 0, t is equal to t naught, and t is equal to infinity. Okay. So how we can solve this question? So let's proceed with the solution. We need to find and interpret the circuit in a way because the diode is here. As you know, diode is forward biased in certain case, and diode is reverse biased in certain cases. Okay, if you can close clearly here when it is in the switch one position, so this P type is connected to the positive terminal of the battery, so it is forward biased. So when uh, when diode is instantaneously switched from the conduction state, it needs some time to return to non-conduction state. So diode becomes as a short circuit for the little time, even in the reverse direction. Now this is due to the accumulation of stored excess magnetic carrier charge when diode is forward biased. So the time required to return back to the state of non-conduction is called reverse recovery time, which is storage time and also transit time. Now what is the storage time? That is actually period for which the diode remains in conduction state even in the reverse direction. And transition time is the time elapsed in returning back to the state of non-conduction. So when between time t is equal to greater than 0 and get less than t naught, so in that cases, my this diode will be forward biased. If it's forward biased, then what will be my current? So it is 20 volt divided by R is equal to 10 kilo ohm, 2 milliampere. And when t greater than t naught, this voltage will be minus 20 volt. Okay, so this is during the storage time. So that means that is between t naught to t naught plus ts. Okay, ts is nothing but your storage time. So what is my current then? So it will be minus 20 by 10 kilo ohm, that is minus 2 milliampere. So during this transition time, that means t greater than t naught plus ts and t naught plus ts plus tt. Okay, id decreases exponentially to minus I naught. Okay, so for t greater than t naught plus ts plus tt, I will be equal to I naught. So if you can take the correct case, current with respect to time. So I'm taking I in the y-axis, current sorry, time in the x-axis. So the correct sketch will be like this. So if you can see, different intervals are there: 0 to t naught to t naught plus ts, then t naught plus ts to t naught plus ts plus tt. So the graph will look like this. Okay. So this is some of the questions based on electronic materials and devices. I hope you understand the concept. Thank you, everyone.